Hello, I'm Dr. Ron Eglin. This is COP 3530 Data Structures, and we're coming here to talk about bee trees. Bee trees. Now, the reason we're going to talk about bee trees is because I get a lot of confusion. A lot of students come to me and say, so, I understand these binary trees with its left and right node. Now, we've got to do something with a bee tree. So what about its left and right node? And the first thing you're going to say is, no, that's not exactly what we're talking about. A binary tree and a bee tree are totally different things. So we're sorry to confuse you by calling them bee trees, but that's what it is. So let's talk a little bit about what they actually are. Well, if we start with that concept that you understand what a binary tree is, which is node, left and right, bee tree doesn't have that left and right as a limitation. They can have as many as they want. Okay, that's great. Why do we have these? Well, let's go back in time to the days when we actually had to really worry about writing stuff to and from the hard drive. You needed to have everything in a specifically sized block because the way that the head of the drive worked is it would chunk down and it would drop a block onto the magnetic tape. And it had a specific amount of stuff that it could put there. Well, what that meant was we needed a way to organize that information efficiently in chunks of that specific size. So that it was like blunk, 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 blunk. And the writing head to the hard drive would work just fine. Well, how do you solve a problem like that? You invent the data structure that solves it. And what was the data structure that solved it? It was the bee tree. Now, I kind of like using this the bee trees are fun for me because I just somehow envision a tree covered in bees. And that's just part of it. I can't really do that with a binary tree. I can't imagine a tree covered in binaries, but I can definitely imagine a tree with a lot of bees in it. All the different types of trees that you're going to use. I mean, binary trees have a rule. The rule is simple. You have a left and you have a right. And those rules can give way to more rules, like all the nodes at the bottom are going to be the same level. Okay, those are just rules, and each time you define a specific set of rules, you really are defining a different type of tree. Those rules are important. And the reason those rules are important is because they define the way that you're going to actually manipulate the tree with the algorithms. If you change the rules, the algorithms have to change. And by having a common set of rules, you can write common sets of algorithms that let you do the manipulation. So we can talk about the rules that have to deal with the bee tree. Now, this would be the rules of the bee tree. Like the root has at least 2 subtrees unless it is a leaf. And each non-root and non-leaf nodes holds k-1 keys and k references to subtrees with a specific mathematical relationship. I'm not going to go into the guts of this. What we're really saying is that you've got a node which can have multiple pointers coming off of the node. So let's look at this bee tree I've got right here and kind of use that to make sense of the bee tree. So you got this top node, okay, and that top node has a 50 in one of its slots. And the pointer isn't actually coming from the 50. The pointer is coming from the head of the node. The 50 is the content that sits in this spot of the node. And everything that has a value of less than 50 is off of that pointer that goes to the left. So what comes off of that is the 10, the 15, and the 20. And if you go to the right, you've got the 70 and the 80. So the node to the left contains 3 content values. The node to the right has 2 content values, and the left pointer of the 50 and the right pointer of the 50 point to those individual nodes. Now, if you delve down a little bit deeper, let's go to the node to the left, and let's look at the 15 because it's in the middle of the 10 and the 20. If you notice, it's sorted. The node is itself sorted. And between the 10 and the 15, well, there's values that can be in that sort between 10 and 15. And those are contained in the next node down, which is the 11 and the 12. Also note, all the leaves are at the same level. Now, if you think about this a little bit, that can be troublesome, because what if we find something that needs to go into one of those, let's say a 22, and let's do that. 22, you go to the top, well, we know we need to go to the left, the 10, 15, and 20. And you know it goes between the 15 and the 20. So you drop down to the 21, 25, 27, 29 node. Okay, wait, that's something messy there. Okay, well, what are we going to need to do there? Well, between the 15 and the 20, I'm sorry, actually the right side of the 20, I've got the pointer in the wrong place, but I'll say the right side of the 20, 21, 25, 27, 29. Just imagine that that's not between the 15 and the 20. Now it's to the right of the 20. The 22 goes in there, but it only holds 4. Okay, glad that I caught that little thing there, which is good because you can actually see these. That's a problem. Got a problem. 22, but it doesn't fit. Okay, what are you going to do? Well, you're going to have to push something up. You're going to need an algorithm that balances the tree, that makes it fit. And those algorithms are out there. They're already written. They're efficient. They're fun to watch, the animations. They're good algorithms, okay? The basics of doing this are relatively straightforward, okay? If you look at like something that actually fits, well, you just kind of move and you fit it to the right spot. But when you run into something that's full, you've got to figure out how to actually do this. I'm not going to show those algorithms, but I am going to tell you they're not hard to find. They're fun. They're actually kind of interesting to watch, and you should actually go through and watch the animations of how the algorithm rebalances. That's if you're putting something in. Well, guess what? Same scenario applies if you take something out. Okay, so before I move on, let's recap just a little bit. The B tree that I just showed you was defined by a specific set of algorithmic rules. It had the ability to put multiple pieces of content into a specific node. And it has the ability to point at multiple nodes below it. Okay, that's the basics of it, right there. Now, the reason I covered the basics is because there's lots of variations. So one of the problems with a B tree could be that, you know, you got a lot of empty space. Okay, 69%, okay, percent empty space. If you just throw in random input, and that's not hard to figure out because you just make a B tree and throw random numbers at it and stop at a specific point and look and see how much has been utilized. Take the average of all those different trial runs and see what you got. Well, what can you do? Well, you can come up with different variations of the B tree, like the B star tree. What other variations have you got? Well, you've got the B plus tree. And why, and I just showed you the reason for the B star tree. That was because it was really empty and you wanted to fill it up better. So you make rules that make it fill up better. The other one, variations, the B plus tree. Well, now we've got this problem with sequential access of the leaves. It's very common to need to go down to the leaf level and need to get stuff right out of those leaves, but then to need to jump to the next leaf over to get more information. Well, the only way to do that with the B tree is to go all the way back up to the top and come all the way back down. We can solve that. Let's just throw a pointer in there. So take all the leaf nodes and there they are. Just pop them in there. And notice that this time, I actually have my B tree part of this balanced very well here. Okay, so a pointer at the lower level, and now I can jump sequentially from each of the leaf nodes to the other leaf nodes, and I've got the B plus tree. There are plenty of trees, plenty of different types of structures, and they all have specific purposes. So when you're designing efficient algorithms or selecting efficient algorithms, you look for the structure that fits the best. If you don't find a structure that fits well, that's when you get the chance to invent your own. So let's talk about one that somebody invented, the TRIE. Again, to confuse you even more, it's pronounced tree. So this is the tree, which is a specific tree, which is a variation of a B tree, but not a binary tree, called a tree. You can see how people might get confused when doing this. What is the tree used for? Now, if you want to call the tree, the tree, by a different name, you can call it the radix tree. Well, the concept of the radix tree was really designed to make spell check systems more efficient. And what do I mean by a spell check system more efficient? Well, let's talk about how spell checking occurs. You look at a word. You type in the letter A, okay? Well, that's a word into itself, but if you look at all the different kinds of words that you can make by adding letters to A, eventually you're going to get some dead ends. So you type in the letter B. Well, now you've just limited down the number of actual possible words you can make because only a smaller finite set of words begin with AB. About, there's that one, okay. Well, now you add another letter, L, okay, ABL. Well, there's still words you can make that start with ABL, okay. Now, eventually, you type in that last letter, and there's no words that you can make with the combinations of letters that you started with. And the spell checker goes off and says, you can't make a word with this. Now, what kind of systems do this that you use almost every day, especially if you have a cell phone, okay? And it gives you suggestions. Well, you want that to be extremely efficient and extremely fast. Because if it's not extremely efficient and extremely fast, they're going to be tapping in letters and your phone's going to be pausing and you're going to have not seeing what you're going to be able to do. We got a structure for that. There's a structure for that situation. The tree. Okay, that was one that, and I'm not going to go back to that, but that's a specific structure for that specific purpose. So, what have we done? Okay, I haven't gone into a tremendous amount of depth about each of them, but we have covered the basic concepts of now multi-way trees. You're no longer stuck in a binary world, even though they're all implemented in binary. They're multi-branches that can come from each of them. And you should be able to look at these different trees and look at the rules that define them and see how they might fit specific applications that you have. Because there are many things you can do. And having the right structure to do it is important. So at this point, we've covered all of lists, and this is the last of trees. And the only thing left beyond here is now we're going to go to the next level, which is graphs. And graphs are when you can actually no longer have to worry about having things that make a triangle to connect together, because trees don't do that. Okay, graphs do. But this is the last of trees. And I hope you enjoyed all the way through the trees. Thank you very much.